parameters so you can judge, the computer can judge for itself what this new problem, the solution to the new problem is. Let me give you a real simple example of that. Simple regression. If you plot the background of folks coming into KAUST, and I'm just making this up. Now those who just have geology only, you know, GPA in the background, you predict your input with an input of geology background only, the GPA at KAUST is going to be modestly lower than some of the other GPAs. If your background is purely math, you get a little bit higher output in your KAUST GPA. And if you have physics as your background, then you get an intermediate level GPA. But if you have the combination of physics plus some geoscience background, you get a pretty high GPA in the ERSE, or the Earth Science program at KAUST. So what they like to do is, the registrars like to get information like this, and when you have a new problem at hand, that is, say, what's your name? Rami. Rami applied, and they looked at Rami's background, and they wanted to predict how well he was going to do. If he fell in this level of GPAs, they weren't going to accept Rami. So Rami's, of course, was somewhere around here, right, Rami?
Yeah.
Where are you? What's your background?
12 engineering.
Ooh, that's way over here. Okay, anyway, that's special considerations. I didn't plot everything. So I guess your Rami's more maybe somewhere in between, some kind of combination, geoscience and math and physics. Okay. So they were able to find, they did a best fit curve on this guy, and they found the slope and the intercept, and then they used those two parameters, slope and intercept, to predict what Rami's GPA was going to be, and it fell up around here someplace. And so they accepted it. I'm just making that up, but that's sort of how they use it. So how did they solve this new, how did the machine learn, solve this new problem, whether we should admit Rami or not? Well, they learned from past data. Okay. That's called simple linear regression in this case, because we assume that our relationship between input and output was linear. Well, you don't just have you have to figure out a model that relates input to output. That's what machine learning is all about. You have to put your foot down and create a model that relates the input to the output. What's your problem you're trying to solve, Shuyu? In fluid. What is your problem you're trying to solve in fluids? And with machine learning, what are you trying to do with machine learning?
You mean right now, or?
Yeah, what's your idea? You have this idea that, oh, machine learning should be used somehow.
There's two popular areas people publish paper in for machine learning applied to fluid impulse media. One is to construct a multi-scale basis function by using deep learning method. Another one is to speed up.
Multi-scale basis function?
Yes.
The basis function is for predicting what?
You use a basis function to construct a finite element method for fluid flow.
Oh, basis functions for finite elements. Okay,
Yeah.
that optimizes.
But the basis function normally needed to be you solve a local problem to get a basis function, but that's expensive. But you can use a deep learning method to quickly generate this based on past existing basis functions.
Okay. So in his case, one of the reasons why he's here is, let's relate that to this problem here. Instead of Rami or someone else with a background, the input, instead of being the background, the input is, Shuyu has done a lot of simulations where he has, his models consist of very homogeneous type materials, and then embedded in that are very complex materials with very strange variations in parameters. As you might know, finite elements or spectral elements will adapt their grid so that where you're going to have real trouble with your solutions not being very smooth, maybe some being very sharp, you need to have a very special kind of grid. And unfortunately, a lot of people just default to having a really fine gridding in that area of complexity. And that's not very efficient. So what they'll do is they'll try different grids and different shapes and maybe sizes for different problems. And they'll figure out the ones that work sort of well, and they'll have a whole bunch of examples of that. So the input in that case would be moderately complex models, really strongly complex models, really crazy models, and maybe models with, that you're trying to model fluid flow in the interior of the sun, say. So, and what they've done is been able to figure out the best type of grid pattern, It might be the density of grid sizes, might be the shapes, might be a combination of the two. And that would be this axis here. Given the type of model, they might have different classes of models, not just based on complexity, but something else. What is the best type of grid? And they find that out by various experimentation. So then he comes up with a new fluid model. That's, some client of his wants to find out, I'm not sure he has lots of applications, as you will know. And it may be something some petroleum engineer wants him to find out, what's the fluid flow characteristics of this kind of salt dome? And what he would do, rather than do trial and error, figure out the optimal grid pattern or the grid shapes or the grid something, the cell size, he would just take this so-called slope, and it may not be a slope, maybe something more complex than that. He'll take those parameters learned from previous experiences and be able to identify, that's a physics plus geo type problem. Therefore, we need this type of spectral element density, spectral element shape, and something else that might associate with. In this case, we have just a 1D type of information, but you have multidimensional information on this axis and multidimensional information on that axis. An example of a nonlinear relationship between input and output might be the happiness index. Because Rami, he kind of traversed this area. He wasn't that happy with his previous life. But then when he realized, if you combine physics plus geoscience, you're a lot happier. And it wasn't him, but we also provide a poll to the students coming in, and they tell us how happy they are at the end of their studies here. So then they try to put some kind of linear fit to that model. That's not going to work, okay? Because anybody in just physics alone, it's going to predict a happiness up there, but it's not really true. But when you learn about physics and geoscience together, then you can get really happy. So the best kind of model for that, you have to assign this, is like a signum function, like a step function. And we're going to be using this type of function a lot in our understanding of neural networks. So they'll just figure out the associated parameters with his signum function and learn from past data. The inputs, the background of the inputs of the students, and the outputs, the happiness index, and they'll figure out the optimal MMB that fit them. And that's a nonlinear regression. Okay, so there's 3 classes of machine learning, and this definition has evolved over time. But the latest definition came about 2 years ago. 2 years ago on the web. NVIDIA, which is one of the leading GPU companies, classifies artificial intelligence as a composite of, it's a general learning method, and embedded in that is machine learning, and embedded in that is deep learning. And this is where we're going to concentrate most of our attention in the course. Neural network, convolutional neural networks. So AI is, you can see the definition, it encompasses a lot of different methods. It's, over the years, decision tree learning, inductive logic, clustering, reinforcement learning, Bayesian networks, among the many methods are out there. That's what artificial intelligence involves. And it not only involves the methods of where you learn from the data, but also where you program your system so that it can do what you want it to do. For example, in the early days of language translation, they would have very strong logical statements, if-then statements, to take your input language, and say French, and then use the logic of grammar and formatting to translate it into English. And that's something that the machine doesn't learn. You actually program those if-then statements with you. When you go to machine learning, this is the area where you learn from the data itself. You don't have to explicitly write a code to do this. And so I just gave you an example of that with the linear and nonlinear regression. And to distinguish it from what we're doing in this course mostly, it's the CNN, and they call that deep learning. And I'll define what deep means in a few minutes. But this is where the revolution started around the mid-90s, but wasn't recognized as such until the early 2000s, when some breakthroughs in convolutional neural networks showed you can solve many different problems. So what is a neural network? Well, they take a neural network. Why is it called neural? Because they take the model from their basic understanding of how our brains work. You have a neuron, and you have inputs, and these are electrochemical inputs along these little lines here, and these are called synapses. And it goes into this signal processing generator in the middle here, and then it decides whether it should pass on the signal from left to right. So this is the traffic cop. And you have an input, and the input could be either a scalar along one of these, the scalar value of the electrochemical potential along one of these synapses, or it could be a combination of these input electrochemical voltages along these synapses. And the output could either be a scalar or could be a combination of outputs as well, a vector. So you can represent this mathematically, how a neuron works by, in this case, it's a matrix vector multiply, where the matrix is the responses to the inputs at each of these neurons, say x sub 1, x sub 2, x sub 3, and that might be the size of the potential, of the electrochemical potential along each of these synapses. The response of that, each of these guys, is given by the weights of the matrix, Wij, and you have a matrix vector multiplication here. And then you get this, whether you pass this input signal along these many synapses onto the right here, is given by this, you might think of it as a threshold function, a sigma. It could be a sigmoid, it could be these other types of functions. And that's the mathematical relationship between the output of this ith node and the input at the various synapses in the input. This thresholding function, if this thresholding function is such that if this is considered to be z, the input, z sub I, say, z sub I is the input here. You look along this axis here, z sub I, and if z sub I is, say, 4, the output is going to be given the value, in this case, 1. And if the input is less than negative 4, then the output's going to be 0. So this is either a thresholding type operation. It could be very sharp, like a Heaviside function, or it could be like this sigmoid function, as you see here plotted. So the problem can be succinctly stated as given the vectors x and y, such that y is related to these guys by this equation. W being the traffic cop. Find the coefficients for W, and this is called machine learning. The set of steps in which one takes to find out what W is that satisfies this equation for all the what they call training examples. For example, training examples in our GPA example, we had lots of people coming in. We had their GPAs before they came in, then GPAs afterwards. Those are the training examples. And from those training examples, you found the slope and the intercept. In this case, the training examples could be, in the case of Shu Yu, many of his input models characterized by, say, the complexity, the density, the type of geology, the type of application could be the input. So any one model could have many parameters to characterize it. And the output being what kind of finite element grid is best used for that particular model, could be the output. So the goal would be to find the W's that decide that. And once you find those W's, and we're doing that by this symbolic notation of W is equal to some inverse operator applied to Y, just like in a linear algebra, that would be a matrix inverse, but it's not linear algebra anymore. It's a nonlinear relationship. And that's neural networks in a nutshell. That's a very high-level overview of what neural networks does for you, whether it's convolutional neural networks or whether it's standard neural networks. Any questions? Ron, to give you an example of applying neural networks to one of your problems in petroleum engineering that was difficult to solve. what's your input? What's your desired output?
Yeah, my input is the volume of my drilling fluid loss.
Your drilling fluid loss.
Yeah.
What does that mean?
When you drill, the mud losses in the formation.
Okay.
So this has cost a lot of money for us. So
Okay. So the input is certain types of geology, certain depths, certain widths of the borehole, drilling rates. Maybe the input is a lot of parameters for one example. And the output is, wow, I had a 20% fluid loss.
Yeah.
Then you took another example. You characterize it by maybe 50 values of something. And the outcome was only 10%. And then you took it to another geology area, say limestone instead of soft, young sands. Then you only had a 5% loss and so on. So you had all these examples, okay? How could you use machine learning to predict what's going to happen when you go to a new area? Well, you take all your input examples, X, each example has 50 parameters associated with it. Depth, geology, width of the borehole. And the output is an output of just one number. That number is fluid loss. So you have a lot of equations, a lot of, you went to different areas of the world and you captured all this data, these different X's and different Y's. And you try to fit a relationship between them for all of them, not just one, but for all of them together. So you try to satisfy all of these examples with one set of W's. Set of W's is big, it's a matrix, those are coefficients. Have you ever tried to invert a matrix with matrix coefficients? No.
I was using MATLAB to do it.
Well, you don't even let MATLAB to do it. You basically, you're trying to find the W's, you're trying to find the matrices. That's something very different than most of you are used to. Okay, so you're trying to find the W's, that huge matrix, and there's ways of doing it. And once you find W, what are you going to do with that? You're going to go to a new example that you didn't train on, and you're going to apply it and get new answers, hopefully accurate answers to the prediction of fluid loss.
Excuse me.
Yeah.
So do you have an example from the field of geophysics? For example, seismic.
Okay. I'll show you that a few slides later, definitely. But right now I want to go outside of what I do for a living. And I think, what's your name?
Lukman.
Lukman. Give me a quick example of what you're trying to solve for.
Okay, so in physics we're trying to find different phases of matter, and this method can be used there. For example, if we
What's your input? What's your output?
Our input can be potential, nearest neighbor potential, the interaction potential, and output can be
Of the atoms.
Yes, of the atoms.
On a crystal plane.
On a crystal plane, the atoms are interacting with each other. That could be our input, and output can be the phase or the energy. Our energy can distinguish different phases, so that can be our output. So I think this method can be used to train the data for some values of interaction, and for the other values we can find the phase diagram for the rest of the interaction.
Okay, so let me try to summarize from what I understand. I talked a little bit with Aurelian, and I looked at one of the papers. I think it was his paper. But he's in material science, right?
Yes.
And you're trying to design materials with special properties, okay? So to find out what these properties are, you need to do these horrendous molecular orbital calculations, trying to find the models that minimize this the Hamiltonian energy. Okay, and that takes a lot of effort in the computer. So they can also find out the properties of these materials by experiments. Are you in the experimental phase or the computational?
Computational.
Okay, so anyway, so it's just too costly to say, okay, if we have this crystal lattice and you have certain types of molecules that are separated by a certain distance and a certain configuration, what's the physical properties of this new material we're going to make? The temperature, melting temperature, the transition phase, pressure, TP type diagram, things like that. Because once you find a certain configuration that's really is a sweet spot for the desired properties, you can then build these materials and do special things with new materials, such as the, superconducting materials at room temperature, right?
Yes.
So they can only do a few examples that they know the input configuration and the output properties, and they like to interpolate in between that. Okay, what if we had a new configuration? I don't want to go through the computations anymore. Let machine learning do it. Make it a grand interpolator. Find the W's.
Okay. I have a question.
Yes.
I think I understand this slide, but that sigma part is not clear to me. What is sigma doing here?
Okay, sigma is a threshold function.
Sorry, it's deciding
Whether we should move this information on the left to the right. Let me give you an example. When you're a kid and you see a shiny stove, you have no knowledge about the world. Your W's are completely all positive, they're huge, I want to explore everything, okay?
Yes.
So if you multiply everything that's positive here with an input of, hey, this input says, hey, beautiful stove, hey, this one says, oh, it's shiny, it's interesting, and this neuron says, touch it, explore it further. To be able to touch it, the output here must be greater than 0. In fact, significantly greater than 0. So when you're a kid, all the W's in your brain are what? 1, right? You want to explore everything. Experience hasn't taught you what to do and what not to do. So if your input is, oh, a slight potential, oh, it's pretty, oh, it's interesting, oh, it's within reach, of course you're going to multiply this W, positive W's values, coefficients, by the positive X inputs, interesting, nearby, within reach. And it's going to give you a big positive number here, right? What number does it give you?
Maybe more than 100.
Okay, 100, more than 1, for 1,000 for you, okay? So you got 1,000 here. Let's look at our chart. Okay, where are we in this chart? Well, this is when the output, say for one output, is not 2, not 4, not 6, but way over here, 1,000. What's the output for that threshold function going to be?
Wait,
It's going to be what?
what yes?
Just tell me a number. We're 1,000 out here. What number do you get for your output? Sigma z.
1.
1.
Yes.
And what does 1 say? Touch that damn thing.
Alright.
Okay, and by experience, what happens is, when you're a kid, you you realize that really hurts. And that's not a good idea. So by experience, these W's now start becoming
0 and
more discriminating. If you see something pretty and it's kind of hot and it's shiny but it's hot, it's within reach, well, one of these guys is going to be recognized as, hey, don't touch that thing. There'll be a very negative W here that will generally bring that to be lessons or way less than 0. Okay, so it's a threshold function. It's the way they found biology to work in our brains at a simple model back in the 50s. Okay? And they did it for cats. Yeah.
How is this different from like classic inverse problem?
How is this different than a classic inverse problem? Well, what do you mean by a classic
look,
inverse
the
problem?
solution
A linear
is-
inverse problem?
Not necessarily, because the solution in the last one seems like just a
A
number.
linear inverse problem, this guy right here, x is not a function of w. Okay, and they call this a linear inverse problem. X is not a function, or w is not a function of the input.
Mhm. So in
So,
this case, the
so
W would change.
in this case, x turns out to be what? A function of w. It's a nonlinear relationship between the output and the input x. W is going to be a function of x. I didn't explicitly put it there, but this is a general notation for showing that. So the inverse is a function of the model. In a linear inverse problem, the inverse matrix coefficients are not a function of the model, the coefficients you're trying to
But the nonlinearity here also includes the sigma function there.
find. Yeah, in this case, you have a
Yeah, sigma is
the nonlinearity of this is controlled by the sigma here. If If you didn't have the sigma, then it'd be a linear relationship between x and y, as long as w is not a function of the input. Turns out w is also a function of the input. Okay, a little bit of the history. The biological model of how our brains work was started out by the pair of people at MIT, McCulloch and Pitts. And eventually, over a period of years, the engineers got a hold of this information and created what we call neural networks. And the IBM in the late 50s created a machine, a computer based on what they call perceptron, a very simple version of neural networks. But it wasn't very useful until they realized something that's not quite deep learning, but you can concatenate several of these neural networks together to get a more complicated system to solve more complicated models. And that was the mid-'80s, and they figured out also how to solve for the coefficients W. And the solution method for finding the coefficients W is really simple. A simple steepest descent is what suffices for most groups. We've been working in nonlinear inversion methods for the last 35 years in my group, and that's the last thing we ever use. It's really one of the bare bones, simple methods out there. And it wouldn't work for our problems, but somehow it works well for their problems. And then in the early 2000s, the convolutional neural network, which was developed, the theory for it was developed in the mid-90s. It started taking off, mainly because of the advent of cheaper computing and some theorems that were proved by a fellow by the name of Hinton up in Canada. And these are some of the Bengio is from IBM and Hinton's is from Montreal. He's at the University of Montreal. And so this is the revolution we now have and we're enjoying with many of our, this is, when you hear about the self-driving cars, it's the deep learning by convolutional neural networks is what does that. And it's partly propelled by GPUs and partly propelled by the fact that convolutional neural networks is several orders of magnitude cheaper than standard neural networks. Okay, so there's 3 types of machine learning. There's supervised learning. And supervised learning is you have a bunch of inputs here. These might be pictures of Shu Yu's different geological models that he's tested with his finite element code. And what he does is takes each model and turns it into a grid of numbers. And in this case, let's assume this is just a black and white picture of a dog. And you decide on a grid spacing of your input. And then you have an intensity value, a grayscale intensity value between 0 and 255. 0 meaning dark, 255 meaning the brightest black and white color. And then you take each of these numbers here in this grid and then turn them into a super vector. That's called flattening. So that's a way of quantifying Shu Yu's input geological models, or your, and you might not have a picture, you might have just a 50 by 1 vector as your input, but those numbers you know how to prescribe. Thickness, the width of the borehole, the depth of the borehole, the type of geology, you have little numbers that describe each one of those parameters. In the case of a picture, you can flatten that into a giant supervector. So that's one of your x, that's one of your x vectors, and that's x sub n, that's your nth example. What's your output? Your output could be a scalar. That is, in Rami's case, it could be 20% or 5% or whatever the fluid loss is, but you might be more interested in the output than just fluid loss. It might be cost as well. How much did it cost to do all this? It might be something else. I don't know, what are the parameters? Pressure, okay, whatever, that are important here. So in that case, you'd have 3 points for each example as an output, a 3 by 1 vector. And each of these slots here, the first slot would correspond to the percent of fluid loss. The second one would correspond to the pressure. The third one would correspond to the number corresponding to the cost of it. But I put a more general output here because more general output is I want to classify the input pictures here. And I only have, 20 classifications of input pictures, what kind of animal they are, dogs, cats, pigs, horses, etc. So there's 20 of them. So the output would have 20 by 1 vector here, and each of these pictures would have a one and only one slot here. So if it was a dog, I'd put the dog here, a 1 there. If this was a cat, it'd be a 1 there, not a 1 there, and so on. What's the difference between this and a regression problem? This is a classification problem. We're trying to classify these pictures. Rami did a regression problem where he had all kinds of numbers on the right-hand side. What's the difference between the right-hand side for a classification versus a regression problem? Rami? A regression problem, you can have any kind of number here. It can range from minus $20 loss to $1,000 profit to whatever pressures. It can range over the entire real line, the numbers on the right-hand side. Classification problem is quite different than that. The output vector has a very restricted range of output numbers in each of those slots. In this case, for this classification, it's either 1 or 0, each of those numbers. So that's the difference between the standard nonlinear regression problem, like Rami would want, or in my case, in this particular case, a classification problem. So when you go to your internet and you say, I want all pictures of dogs, Google will have a W already trained that can classify pictures according to the type of animal it is. And it'll go through all the pictures, these W's. The hard part is figuring out what the W is. What Google will do, will take that W and go through all the pictures out there in the web and then classify which ones are dogs, which ones are cats, which ones are animals, or maybe not an animal at all. And it'll pull up all those pictures that you asked for. A geoscience example of this would be you'd like to have input data and you want to get rid of 90% of your interpretation staff. That's a big cost for an oil company. Is to take a seismic example. This is a seismic image, and this is X versus Z. This might be 10 kilometers deep and 50 kilometers wide. And these little wiggles here correspond to the reflectivity of your subsurface. So if you have a really strong contrast between one layer and another, and its underlying layer, like sediments over salt, you have a giant reflection, very strong reflection, and that gives you rise to this very strong black area here. And you don't want to spend a lot of money and time interpreting where the salt is and where the oil deposits are, so you train a network to do the interpretation for you. And the output vector here is a classification problem where you classify the geology according to these different colors, 1 through 12. And the colors correspond to whatever you think is geology in that area. Soft sediments, old sediments, hard sediments, limestone, shale, et cetera, et cetera. So this is an input, and you train this, you get an interpreter to train, take a bunch of examples. This is the nth example. This happens to be one example. And you color code it to what the interpreter says it is, and you take all these examples, you find the W's, and what are you going to do with these W's with a new example, Rami? You get a new example. Say this example down here. You've already trained your network, maybe over 10,000 different examples has already been interpreted like this. You found the W's, the best W's, that somehow make the input agree with the output.
The inverse the W.
Well, the inverse W's, you already have that. So what are you going to do with the W's? You already found the W's. What are you going to do with it? With a new example that you've never trained on? You're simply going to apply the input X times W. X, this is the X. You flattened it. You have the old W you trained on. You multiply it by it, and then you do a thresholding. And what's going to happen? You get a new interpretation without going through the pain of trying to find what the W's are. You've already trained on the W's. You've done all the hard work. Now you can use these W's and get rid of your interpreters. Is that okay? It's okay to fire all these people, Rami?
That's the new order. That's the new order.
Yeah, that's the new world. That's why all of you should be taking machine learning course, because if you're gonna get a job in the future, I almost guarantee you in 5 years, they're gonna choose between person A or person B, and who's ever had some machine learning experience, I think they're gonna probably if you're equal in other areas, but you have machine learning experience, they're probably gonna choose the one with machine learning experience, yeah.
Could you just please go over the example again, because I kind of lost something.
What?
Can you just go over the example again, where you had the new seismic section and you trained the machine?
Okay, so this is the training, one of the many training examples, where we took, Rami used to be an interpreter. And Rami took this, and he knew there were 12 categories of geology here. And he took his pen, digital pen, and color-coded. The first one is the yellow geology, the second one here is, whatever that is, green-gray geology, blue geology, blah, 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 blah. And he did this over 20,000 examples. And with those 20,000 examples, he was able to find the W by this method that I'm going to describe later. You can do it. Those are fixed. It's like your slope and your intercept for GPA estimation. You got the M and you got the B's. This is the M and B's you're trying to find. And once you found those W's, you're now in a new area of the world. Where are you from, Ronnie? What area of the world?
Saudi Arabia.
Saudi Arabia?
East, yeah.
Okay, so you go to the Red Sea, the unexplored portion of the Red Sea. And they find some new seismic data there. And they quickly want you to interpret this without going through the pain of a digital pen. In fact, they fired you, so they don't, but they have your W's. What are they going to do, Rami, to get this picture on the right-hand side?
Get the W automatically.
Get the W, turn this into a big fat vector, right? Big long vector, a super vector. You know how to do that, flatten it, right? Right?
I don't know.
Okay, let's do it. Let's get that concept clear. Okay, they break it up into this grid of numbers, okay? And they take the average reflectivity here. What's the average reflectivity here?
0.6%.
0.6, okay. What's it up here?
What?
No,
0.9.
No, that's about the same, right? This looks-
Okay.
And what's this? And what's this?
0.3.
Well, oh yeah, okay. Because this is dark, right? Okay.
Okay, so
Okay, that's fine. Okay. 0.25, 0.1. Ooh, wait a minute, these should be, okay. These are normalized intensity values. Remember I said it's between 0 and 255? Okay. Well, you normalized it, okay? What's this? 0.1, 0.06. Okay? Let's turn that into a super vector X. Rami, tell us how to do that. How do we turn this picture into a super vector input X? What's the first element we put here?
0.6,
0.6. What's the second element value?
0.6.
What's the third one?
0.6.
Then what do you do?
Then you go left, yes. 0.3, 0.25,
Super vector. But he has, in his training example, he has another training example, right? You do the same thing. Okay. Well, first off, you have this, and it's related to geology. So what geology is this up here? Is this a 1? Now, let's say, we have 12 numbers. So what geology is this?
mixed ecology. Let's say it's weather.
It's an in between 1 and 12. So what geology is this?
We'll go with limestone, for example.
Okay, so what's the number for limestone?
6.
Very good. It looks the same, right?
Yeah.
6. This. What's the geology for this?
Sandstone.
7. Okay, what number is sandstone?
Honestly, no, I don't know. 9?
No? Okay. 9.
9.
Okay, whoops, go back to 6, okay? So Rami spent a long time, he used his knowledge of interpretation and going from this picture to the interpreted picture. This is a classification, nonlinear classification problem. But he's not through yet, because then he's got another set of equations, okay, from his other picture, and he just adds it onto here if you want. So you have this huge supervector input, huge supervector output. Now there's different ways of assembling this in format, but I'm just doing it for. Okay. So you've got this giant set of equations you need to solve. What are the W's that best explain the input and output relationship? You have a model for that. That model is this. W dot x equal to y. This is the y. This is the x. And you find this giant vector W.
So we need W that will define all the inputs simultaneously at the same time. So there will be many equations that will be used to find W.
So Professor, I have one question. So since we already know the correlations between the rock types and the intensity parameters, why do we still need to find the W? You know 0.6 refers to what's the formation? -3 is sandstone, you know that. Why still need to learn?
Okay, so that's a good question, because everyone get what his point is. Okay, there's a one-to-one relationship between intensity value and geology. Anytime you see a 0.6, it's got to be limestone. Did you say that was limestone?
Yeah.
If that was the case, we wouldn't even need to hire Rami. We can fire him even before. Why? Because you can classify limestones and sandstones or whatever geology just based on intensity according to what's your name?
Wait.
Wait. Okay, Wei says you can do that, right? You don't even need Rami. Get rid of him. He's worthless. And then once you have the W's, just you can start doing this, or just do that one-to-one relationship. What's the problem? That's going to stop us from firing Rami so quickly.
Because you don't always have 0.6.
Yeah. You don't have this one-to-one relationship.
But even you have a corresponding range is also fine. You say 0.4 to 0.6 refers to limestone. Is also
Even
fine.
that's not unique. You have probably a 0.3 to 0.7 relationship for sandstones that are old sandstones. So it's not a unique relationship between intensity values and geology. Because this geology, if you look at these intensity values here, they're just, it's between, all the way from here to here, it's probably between 0.1 and 0.2. Yet the geology can vary dramatically. Depends on the age, the depth, et cetera, of this environment.
And then I think also for training the neural network, you need many data, label.
Yeah,
so
you need many examples.
Many examples.
This is
are
called
labeled
one
by
example.
experts. So
Yeah, I can guarantee you that I can give you a picture that looks almost identical to this from a different part of the world, looks with intensity values about the same range, completely different geology. This is shallow, but this other area that looks almost identical would be very deep in a different part of the world, different type of geology. So we can still keep Rami until he classifies everything. Then once he classifies everything in Saudi Arabia, we get rid of him. Why waste money? Because we have his W's, his legacy.
So this W is not necessarily going to work outside Saudi Arabia.
What?
They're not necessarily going to work outside Saudi Arabia because they were like.
Well, where does Aramco explore? China? No. No, they explore Saudi Arabia, period. Okay? So we don't care. So what's the problem with firing him so quickly? The problem is this. The managers look at this and they go, there's no traps. We don't need to explore for oil here, right? They found the W's and look, there's no traps there. But to their dismay, when they had an expert just go back and check to see if this interpretation was right, created by the machine, they found mistakes. The machine missed these faults, and faults are called traps in geology. That is, oil will come up to these faults and they can't go any further, they accumulate there. That's where they usually drill, at least in structural environments. So that emphasizes a certain point here. Machine learning is not perfect. It's never perfect. You're never going to get more than about 90% accuracy in at least the geology problems we're trying to solve. And if you're not happy with that, then don't use machine learning. But guess what? If I went back in Rami's history of interpretation for the oil companies, out of the 10 prospects he recommended to drill, 3 were dry holes. So what's the success rate?
70%.
What's the success rate of machine learning? It's less than 100%. So I think we're approaching the type of accuracy that even humans can have now, machine learning in certain areas of it. Now, for, I forget your name again?
Lukman,
Lukman. Okay. Where are you from, Lukman?
Pakistan.
Pakistan, okay. Lukman. I don't know if he could tolerate having an error rate less than 95% when he claims he's got a new material, superconducting material that is going to superconduct at room temperature. Okay. He probably could tolerate it, maybe once or twice, so maybe he can tolerate a 9% accuracy rate. Because then what you do is you don't announce to the world this result, you go ahead and test it in a lab and see if it is superconducting at room temperature. If it is, bingo. And if you're right 9 out of 10 times, bingo. You know what bingo means?
Bravo.
What? Yeah, bravo. Yeah. Okay. Then there's this unsupervised learning method where you don't have to spend a lot of money on Rami anymore. You just insert the data and it organizes the data in different groups for you. And the simple example that, I'm going to lose probably about half of you on this, is common shot gather, X versus time. Notice there's different shapes here. The different shapes are associated with the different slopes of the lines. Most of the slopes along this red line are flat. Most of the slopes along the yellow line are steep. Turns out this is perfect to reorganize this. Right now the red and the yellow are crossing each other and they're kind of messy. But if you take an FK transform, a Fourier transform in the X and T directions, it'll reorganize these slopes so they're not crossing each other and they're easy to get rid of. The good from the bad. It turns out the red is one of the colors is good for seismic, the other color is bad. You can easily separate the two out and get rid of them by an easy filter. This is called an unsupervised learning method. But mathematically, the input is given by X and the output is, you don't know what the output is. You don't need Rami to classify which is red, which is yellow. You just simply have a transform that separates the two types of data based on some feature associated with the transform. The transform doesn't have to be an FK transform. It could be a radon transform. It could be like a Bohr transform or Huff transform. All these kinds of transforms that can go. So the beauty of this is this costs a lot of money for the training set. This doesn't. It's free. So it's quite limited. And some of the methods here are PCA, SVD, cluster analysis. And this is a example of data, geoscience data, Old Faithful eruption duration versus eruption waiting time. That is, there's a place in the United States, it has a bunch of geysers, and there's this geyser that erupts every so often. That's a regular eruption. But if the eruption only takes place over a short period of time, the duration, then you don't have to wait very long for it. So say if the eruption only for 20 minutes, you only have to wait for an hour, every hour for it to happen. But if the eruption lasts a much longer period of time, say 5 hours, then you're going to have to wait a lot longer for it. But you don't quite know how these eruption cycles are segregated from one another, but a machine learning method, and that one we call clustering, will allow the machine to automatically learn which are short periods of time that you don't have to wait too long, and which are long periods of time where you see a lot. And we'll learn about that clustering. So that's an unsupervised learning method. Finally, the reinforcement learning, we won't go over that very much in this class, but this is where the chess masters, they train their network W's, find the W, where you don't really know how to get there to the output, but you do have a grade that allows you to to say whether you won or lost, and this is in the context of games like checkers or chess. At the very end, you know whether you won or lost. And they'll just insert these moves of inputs of the starting features, and they'll track each move for some chess master or go master, and they'll find out what the moves are, and from that learn the right W's that relate the best moves to give you outputs of wins. In this case, for checkers, the output would be the final set of pieces on the board, where the ones would belong to the whites and the minus ones would belong to the reds here. And if the output is all ones and no reds, it'd be 1, 0, 0, 0, 1, 0, 0, da, 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 da. And so you can grade that, and the grade is maximize the sum of the outputs. So if there's more ones than there are negatives, then that's it. And they'll find the W's that way. Okay, so of these three methods, we're going to learn about 3 of these methods in our class, unsupervised learning. And we'll learn 3 supervised learning methods, but this is the one we're going to use for most of our projects. Yeah.
Excuse me, so regarding the unsupervised learning. So
What?
who will teach regarding the second method, which is the unsupervised learning? Who will teach the machine which one is right, which one is wrong? So when we go to the theory, for example, domain, and we have the relay and the reflection,
Yeah.
probably the machine will take the reflection as noise, or it will get rid of it. So
Well-
who will teach you which one is right, which one is wrong?
Okay, in this example over here, so how do you decide which one's good, which one's
Exactly.
wrong? That's up to you. The machine is done once it separates these two guys. Now it's easy for an interpreter to go and say, okay, this is noise, this is signal, or vice versa.
So it doesn't decide.
It won't decide that. You could build it into that anything with a dip less than this yellow, or about yellow or less, just mute it out. You couldn't do that over here, because they're tangled up they're intersecting.
So the decision is only with the supervised learning. Undecided methods is the unsupervised.
Yes. Okay, so I've already gone through this example of the cat and dog. If it's a dog, you put a 1 here. If it's a cat, get rid of that 1 there and put a 1 there. And it's up to you how many classifications. What's the difference between a supervised nonlinear regression method, or I'm sorry, a nonlinear regression method and a nonlinear classification method? What's the difference between the two? Robbie? No. What's the difference between a nonlinear regression method and a nonlinear classification method?
So the regression have wide range of solutions.
Each of these numbers could take any value along the real line for a regression.
Yeah. And for the classification, it's very limited.
It's restricted. So a very small set of numbers on each end. Okay. And then once you find the W's, this is the algorithm. You have a new picture. You want to classify it. What are you going to do with that picture? You're going to take your learned W's, W, and multiply it by the new X vector, and that'll give you a classification. Now, is that classification just nothing but zeros except a single 1 here? No, typically you'll find out later. It'll be 0.6, 0.1, 0.02, point da, 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 and you pick out the largest number there for your classifications. Even though your trained right-hand side is either zeros or 1s, your actual output is going to be typically kind of a variation of numbers between 0 and 1. And those can be considered as probabilities. You pick the one with the largest probability. You'll see what I mean by that later. Okay, in detail, let's connect some math to our pictures here. If you have one picture, you get one equation because W dotted into this set of W's that connect this to this guy is given by W1, W2, dot, 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 dot. It's a dot product. In W and X, you can give you an output Z. And then you have a predicted value of that. And you can symbolically represent this guy by this picture here. These W's correspond to each of these nodes, the values of each of these, or I'm sorry, the X's correspond to the input numbers in each of these black dots here. The weights of our neural network correspond to the W's here we see. And the dot product of the W times the X gives you the Z, and then you threshold it. In this case, we have how many unknowns? Well, there's n W's that are unknown, but only one equation. We need more equations. So to create more equations, we need more pictures. And then we have a classic minimization problem where we have predicted output subtracted from the observed output, the classification. And we have another picture here, given by the red. We hit it with another dot product of W's, unknown W's. Those red arrows correspond to the weights of the W's. That gives us another equation with new unknowns. And then we hit it with the thresholding function. And the output is either, we're going to have a binary classification. It's either yes, it's a dog, or 0 meaning it's not a dog. We're not going to say whether it's a cat, a mouse, or whatever. Whether it's going to be a dog or not a dog. So the output is that. How many equations are here, Rami?
2.
How many unknowns?
1.
What are the unknowns?
Yes or no?
Well, no. The unknowns are the W's. How many unknowns are there? How many unknowns are there? 2
N.
Cap n. 2 equations and cap n unknowns. Is that enough equations to solve for this? No, it's an undetermined system of equations. So you need a lot more examples. If the first equation is represented by this guy, and by the way, this node here is our neuron, and I symbolize the 2 operations, 2 very simple operations. Matrix vector multiplication given by this sigma, and then followed by this thresholding symbol.
Professor, I have a question.
Yeah.
So, how can you determine the number of the training set? Let's say, just for example, if you have this classification.
The number of examples, training.
Yes, the number of examples. Can we say, like, for example, okay, let's do a permutation, put a permutation, and then take a combinatorial, let's say, because these pixels has a possibility between this intensity until this intensity, and then let's say if this intensity has a correlation with the other pixels, and then take a permutation of those things, maybe just roughly estimate, so somehow your system will not be underdetermined or overdetermined system.
So the main question he's asking is, how many examples do you need to be able to usefully solve this system of equations?
Yes.
Obviously, 2 equations with 1,000 unknowns is not enough. So what's the minimum number of equations we need to solve for 1,000 unknowns?
1001.
1,000. But it turns out in geosciences, and probably every other field, it's an inconsistent set of equations, and it's an ill-posed set of equations. We'll define what that means next time. So you need many more than 1,000. And it's trial and error experience, how many you need. And there's a way of testing that at the end. We'll get into. So anyway, so the second set of equations symbolically can be given by this. We have the same input, x1, well, actually we have a different set of inputs, x1, x2, that are tildes, or the red x1, x2, x3. That's a different picture. We have a different set of unknowns, w1 tilde, w2 tilde, and so on. And each of the new inputs is given by the different weight here on the red pieces there. And that set of equations can be given by that. Two systems of equations. We have n unknowns for this first row and n unknowns for that. Wow, every time we have a new picture, we have a new set of unknowns, right? So we have to keep doing this. Are we ever going to come out ahead and have more equations than unknowns? Yes, we're going to have to get a system of equations. We fix the number of, at least the number of columns here is fixed. But we have many, many more equations. So this is going to be a rectangular matrix. It's very tall but very skinny. That's called an overdetermined system of equations. Right now it's not that. So it's not just a matrix vector multiplication, it's also a thresholding function. We apply that to both sides. And so this set of equations in algebra is given symbolically by this neural network architecture. Except the output is given by one node only. Any questions on this?
W1 and W1 tilde are different.
Yeah.
I'm still not sure. And if we add a third one, would it be like
Double tilde.
double? Then
But that's going to be really ugly notation. So we're going to have a matrix notation for this. Well, this will be W sub 1, 1, W sub 1, 2, W sub 1, 3, da, da, da. So you get rid of the tildes.
yeah, but I still don't see how it's gonna be in overdetermined because it seems like you just add a new unknown, but no enough new equations.
Well, you keep the number of columns here fixed. And you notice that in this case, if you have a new set of equations, I mean, a new picture here, you're going to have another column right here. Okay, and another column, yet you're going to have the same set of equations. This is for, say, one picture, and we have a system of 2 by n matrices here, but then you're going to get another set of x1s here. If you have another picture, you're going to have another column here. You'll see the notation later on. Where we have we have many fewer unknowns and equations.
So what's just not one row times n columns. Talk about the W.
Say again?
Yeah. What is just 2 rows? What is not only 1 row?
What is what?
Now we are multiplying the x's by w's. In the vector, we have over there. We have W matrix multiplied by a
W matrix
exactly multiplied by x.
multiplied by one picture.
Exactly. Why it's not just 1 row multiplied by that column? Why do you have two rows, which is W and W tilde?
I'm not
Because
sure.
you want to get 2 outputs, Z1 and Z2.
Okay.
One W.
Yeah, this is Z1 for that output, and this is Z2 for the output. But there's only one classification of this picture, and that's going to be either a dog or a cat for that one picture. For another picture, we'd have another set of equations just identical to this, except we have a new x1 there. Okay, and then we have another classification. But it'll use the same W's as before. Okay, how many W's are here? 2n, right?
Okay.
There's 2n W's here. So we're going to have thousands of picture examples with the same number of W's that are unknown. So we're going to have an overdetermined system equation. Okay, so this is one picture. And we have a 2-node network. We're letting 2 neurons decide whether we're going to touch the stove or not just one. We're going to let 2 nodes decide whether this is a dog or not. And why are we including more nodes? Because one node might not be enough to decide whether we should touch the stove or not, or make the relationship between the input and the output. It might not be complex enough. You want to put more complexity into your neural network. And you put more complexity in your neural network by bringing in greater brain power. More nodes in your brain are going to make the decision whether it's a dog or a cat. Yeah.
I'm still not clear that each time you add one more picture and you add one column of x1 to xn and you have another row of w.
Let me go back. I think I might have confused you. Can we wipe the slate clean a bit? One picture. This is not complex enough. One node is not complex enough to make a decision, to explain the input and output. So we put in 2 nodes to make that decision for one picture.
So each node will have a w1, wn, which is n unknowns, and 2 nodes will have 2 n unknowns.
We have 2 n unknowns now for one picture.
Yes.
But then we also want the same set of w's to explain this classification. So that a different input, a different set of x's, but the same w's.
Okay. All right.
But then we still don't have enough equations to find all of them. So we take a lot of pictures and let the w explain a lot of those pictures.
So if you only have 2 n unknowns, you need 2 n pictures.
At least 2 n pictures. But in practice, many, many more times.
So can we think about it as reducing it from n to 2?
Say again?
Reducing the number of equations from n to 2 with this process? We still need to classify to yes or no after we have the 2 outputs. Like what do we do with the 2 outputs? Like here in Z. What do we do when we have the 2 outputs?
Well, I don't care what these z's are. What I do care is the final output.
So there's an other like...
Yeah, this is, another thresholding operation applied to what came out of this node or what came out of that node. So we're making 2 nodes. We only have 1 neuron. We can make a decision whether to touch the stove or not. But that's not complex enough to explain complex inputs with complex outputs. We're going to put another node in our thinking process. And each of these nodes is going to have an output, a Z1 here, or a Z1 here, and a Z2 here. I don't care what those are. What I do care is what my final my final decision is in this case, this binary output.
How do we jump from the 2 decisions into the final?
We jump. Here's my 2 decisions. I don't care about those 2 decisions, Z1 and Z2. What I care about is I take these 2 guys, and what I'm going to do, and I'm not showing this, I'm going to sum them up. I'm going to threshold them and sum them up. Okay, and that thresholding, I think I'm going to put a symbol there. It's going to be a summation of those, a weighting and a summation of those guys. And those weighting, the new weights are W1 and W2.
And they're different from the W1.
Yeah, these are black and red. There, I put the threshold on there. Okay. So what is even more complex? Say in the case of Rami's case, he's got a really set of some strange relationship between those 50 parameters, which serve as the input to a drilling exercise, and the output of whether you have loss or not, or 20% loss or not. What if it's more complex than just what 2 nodes can offer you? What are you going to do? There's only 2 neurons that are going to make that decision for you, and you're not getting good results. Increasing the number of nodes or the number of unknowns. And there's another option. You can increase the number of layers, which is almost equivalent in terms of bringing in a new number of unknowns. So there's the option of increasing the number of neurons per layer, or increase the number of unknowns by increasing the number of layers. Both of them have demerits and merits. But the preferred option today is increase the number of layers. And if you go beyond 5 layers, they typically call that deep They couldn't do this 20 years ago. It's too expensive for neural network. But convolutional neural networks and GPUs and fast computers allow you to put more and more of these banks of layers. Okay, so let me finish up. Oh, what is convolutional neural networks? Instead of a W matrix times X here, convolution of X with a filter we call W is nothing but a much cheaper version of matrix vector multiplication. What's it cost to do a matrix vector multiplication? If you have an n by n matrix, to do a matrix vector multiplication costs you on the order of n squared operations. But a convolution matrix times X, if the convolution filter is very small, on the order of, say, 3 or 4 filter lengths along each row here, what's it going to cost to do a matrix vector multiplication, n by n matrix?
And set of operations.
On the order of n times whatever the length of your filter is. If it's 3 or 4 pieces long, n times 4, compared to n squared.
Isn't it n cubed?
You're thinking matrix inverse. Okay. So convolution of neural networks, they found out that you can approximate this WX matrix multiplication by a convolution and go from n squared operations per matrix vector multiplication to on the order of n. That's orders of magnitude cheaper. It allows us to do problems with deep neural networks. And so deep neural network, well, not really deep, is this picture right here. How many layers are there, Rami?
2.
Instead of 1? How many nodes per layer? Is this deep learning, Rami?
Yes.
No, it would have to be greater than 5 or 6. So it's not quite deep. So let's stop there, and well, next time we meet, we'll finish this up, and then we'll also start on the details of the mathematics associated with solving nonlinear sets of equations, and overdetermined sets of equations. Any questions? Yeah.
The projects, will you assign us the projects, or I can?
We'll have an interactive session on projects. If you have a good project, I know you do, we'll design that. Those who are kind of lost, I have very simple projects. Those who are in between, yeah. What's your name?
Marco.
Marco? Okay.
So I was asking if the projects is going to be, which kind of a package are we going to use to implement it?
We're typically, you have a choice, either Keras or MATLAB. And if you're really familiar with some of this stuff, you can use the more sophisticated TensorFlow pad. I don't know if any of you have experience in TensorFlow, but Keras is kind of a MATLAB version of TensorFlow. So, before we end, say back time. What are the important points you learned here? How many types of machine learning methods are there? 3 classes. What are they?
Supervised and supervised and reinforcement.
And what 2 methods are we going to learn about in this class?
Supervised and unsupervised.
What's the cheapest method in the world to use?
Convolution.
Unsupervised, because you don't need Rami to do the classification. Okay. Or other regression. What else we learn? What's a simple operation? Given, describe neural networks in 3 phrases. Given, find, solution. What's given?
X.
X. What's X?
Inputs.
Image.
I said neural networks. Is X the only given?
Image.
X and Y
X and Y.
Yes.
for the training phase.
Yes.
Given X and Y.
Yes.
How many of those do we need?
A lot.
Lots.
A lot. More than overdetermined. How do we know for sure? Do we have enough? Trial and error. Okay. Step 2, find. What are you trying to find?
W.
The W that explains the X, the input and the output. Is this a linear or nonlinear relationship?
Nonlinear.
It's crazy nonlinear. I mean, it's a simple ideas. It's just what seems really complicated. Everyone starts inventing their own crazy architectures up here. You're going to see really crazy stuff going on. solution. X or W is equal to what?
X inverse Y.
X inverse Y. That's it. But you've never done X inverse Y. Why? Because you're finding the coefficients in the matrix now. I bet none of you have ever done that. You're just finding the inverse. You've already given the W's. Most of you have experience just giving W's. Find W inverse, big deal. That's kid stuff. Here we're giving you X and Y vectors, and you're doing the impossible, finding the W, the matrices of W's. And that's all it is. So I guess I don't need to teach anymore. We just see you at finals times, and you guys, that's all it is. It's just details that you're going to get killed. Okay? Okay, so see you Tuesday. And those who would like to, can I have that paper? Those who want to go to the 300 level credit, we'll try to arrange that for you. Wednesday, I'm going to give a slimmed down version of the same lecture. Who wants to have a who else wants 300 credit for this? Yeah.
I have to talk with my advisor.
Talk to your advisor, and like I said, we need at least 1 or 2 more people to sign up for credit for this by next Friday. Otherwise, I'll have everything. Oh, 4 o'clock for the Wednesday. DL, distinguished lecture. It's a geoscience lecture. I don't think. So you probably 对。你就跟他说你选这个课，然后把它补课就行了。Say again. 如果你想上这个的话。You don't have to program your own MATLAB. We give you MATLAB.
So my plan is this is now is as a 300 and just stochastic.
You pick up. We give you the MATLAB. It's your job to change the.
Oh, okay, so so is in a math program.
For example,
Yeah, I'm
good.
Actually, I will really think about my
I took the SS and I failed all of the mathematics process.
You what?
I failed the mathematics and also I failed the physics, so I will take them.
Okay.
Maybe just to make sure that I'm on the right path. Is it okay just to take this course with those?
Well, do you know simple things like matrix vector multiplication?
Yes.
And dot products, and you know basics of linear algebra, how to take an inverse by a direct method of a matrix.
I need to Google it. It's very simple.
Yeah. Okay. Okay. If you've already covered that, you know, I think you're fine. Just as long as you know basic linear algebra, and we'll teach you what you don't know on Tuesday about overinfinities. How to solve it. Okay. I think you'll do fine.
Because I worked for 3.5 years.
For Ramco?
Yeah, I graduated 2016, so the last mathematics course was 2015.
Okay.
Just to make sure, it's okay to take this course with no experience, let's say.
I think so. I think it's okay. Fine. Yeah. I go pretty simple. Now at some point we start, you know, moving ahead pretty quickly, like in November. But by then, you know, you're going to be mainly judged on the first 3 months, not the last month. You really go quickly in terms of your grade and stuff. But be careful, don't overload yourself with courses this semester if you can help it. It's unfortunate. You have to take these background courses. How many? Three?
Three calculus, the differential equation, plus the differential equation. Linear algebra.
Well, this would be a good way for you to reinforce what you learned in linear algebra. So, I think you should give it a shot.
In addition, I'm taking also C++ course in computer science.
Okay.
In addition to this course, so I have total 15 credits.
How many?
15. 5 courses.
I'll try to be easy on you.
Thank you very much. Have a good day, Dr.
I just want to register for this course.
Okay.
So then I will come back to cancel another course.
Okay.
My
Okay, good. What is your name? What's your name?
My name is Xiaoyu Feng, and
Shall you?
yeah, Xiaoyu. So, is it possible for me to change this to a 300
Yeah,
level?
yeah. Well, what you'll have to do is have a more sophisticated project. Okay, and that'll be good for you because are you a PhD student? Or,
Yeah, yeah.
Okay, yeah, because then that could possibly lead to a paper publication, and then
Okay.
you want that. Okay, good. Okay.